Weakly star-G closed sets. Well, in this presentation we continue our survey of these classes of subsets which are stronger or weaker than open or closed sets. These matters are considered in the context of usual topological space. Hence we assume that empty set and the whole universe are open, and we have closure under finite intersections and under arbitrary unions. Well, as we already know, if we have a topological space, then a subset A is called alpha open in this case. If A is contained in the interior of the closure of its interior, and so on, semi-open, pre-open, beta open or semi-pre-open, and regular open in this case, if A is equal to the interior of the closure of itself, of A. All these classes, we also know that all these classes have their counterparts expressed in terms of closeness or closure. So we have alpha closed, semi-closed, pre-closed, beta closed, and regular closed sets. Okay, and now we introduce the notion of hat G closed set. We use this small word hat is because the symbol in LaTeX is hat. Hat G closed set. They've been introduced, as you can see here, by Vera Kumar, yes, in 2000. Okay. So we say that A is hat G closed if a closure of A is contained in U wherever A is contained in U and U, capital U, is semi-open. And of course, as always, the complement of a hat G closed set is called hat G open set. And in 2014, Indira and Meenakumari have introduced so-called weakly star G closed sets, W star G closed sets. And the rest of this presentation will be based strictly on their paper and their results. However, sometimes we shall discuss some examples in a more detailed manner. Be as it may, a subset A is called, as you can see here, weakly star G closed if the closure of interior of A is contained in U, whenever A is contained in U, and U is hash G open. Hash G closed and hat G open and hat G closed sets were here, and here we have weakly star G closed sets. Okay, for example, let X be ABC, very simple universe which consists only of 3 elements, and we have the following topology: empty set, the whole universe, singleton of A, singleton of B, and AB. Now we have the collection of closed sets. It's here. There are complements of open sets. Then semi-open sets, hat G open sets, and weakly star G closed sets are here. You may perform all these calculations. You should do it. But let us check some cases at this moment. For example, this subcollection AC is semi-open because its interior is A. Yes, the greatest open set contained in AC. And the closure of its interior, closure of singleton of A, is AC. Well, and now AB is hat G open, since its complement, namely singleton of C, is hat G closed. This is because singleton of C is contained in the following semi-open sets: AC, BC, ABC, and moreover, the closure of singleton of C is equal to itself. Okay, you should compare this reasoning with these definitions, of course. And finally, consider singleton of C again. It is weakly star G open because the closure of interior of C is equal to the closure of empty set, because As you can see here, um, there are no non-empty open sets contained in the singleton of C. So this closure of empty set is empty set, and of course empty set is contained in each set. Hence also in each had G open set U such that singleton of C is contained in this U. Among other things, one can prove that if a subset A of a topological space is closed, then it is weakly Stargy closed also. And the converse is not true. For example, consider X equal to ABC with the following topology. And now we may prove that singleton of B is not closed. Well, since its complement AC is not open. Yes, we do not have AC among our open sets. However, singleton of B is weakly Stargy closed because it's contained in the following had G open sets, B, AB, and X. Of course, you should calculate, you should find all these had G open sets, all these semi-pre-open sets, semi-open sets. These things have been performed by our authors in their original article. Yes, so you may compare this reasoning and these facts with their original example. And now closure of interior of the singleton of B is again closure of an empty set, and it's empty, and empty set is contained in any set, as we know. Attention, it seems that our authors wrongly state that in this case, in case of this universe and this topology, singleton of A is weakly Stargy closed. However, note that singleton of A is contained in the following had G open sets: AB, yes, here, and X, while the closure of interior of A, of singleton of A, is equal to the closure of singleton of A, but this closure is X. Yes, the smallest closed set in which a singleton of A is contained is the whole universe ABC, namely X. But X is not contained in singleton of A nor in AB, of course. So maybe it's their typo mistake. We also have other relationships. If a subset A of a topological space is regular closed, pre-closed, alpha closed, and star G closed, which means that the closure of A is contained in U whenever A is contained in U and U is had G open, then it's also weakly star G closed. The converses of the above theorems need not be true. And our authors give us some counterexamples, of course. On the other hand, each weakly Stargy closed set is GSP closed, which means that semi-pre-closure of A is contained in U whenever alpha is contained in U and U is open. And U is strictly open, yes? Semi-pre-closure, this notion refers to the subclass of semi-pre-closed, so beta closed sets, yes? And of course, the notion of semi-pre-closure is analogous to the notion of closure, but in terms of semi-pre-closed sets. Well, of course, there are also many other properties. For example, if A is nowhere dense, then it's weakly Stargy closed. We may prove this fact, and in fact, we use this property, or we had some examples of this property. Now, if A is nowhere dense, then its interior is empty by the very definition of nowhere density. Now let A be contained in U, where U is had G open. Clearly, closure of interior of A is, in this case, it's equal to the closure of an empty set. But this closure is empty, and it's contained in U, of course. In fact, in each set. Some corresponding results and relationships can be obtained for weakly star G open sets, weakly star G open sets, which are complements of weakly star G closed sets. For example, every alpha press star G open set is weakly star G open, but not conversely. And on the other hand, each weakly star G open set is GSP open, but not conversely. And in case of GSP open sets, we speak not about semi-preclosure of A, but about semi-pre-interior of A. So that's all. The rest is in our bibliography, especially in this paper by Meenakumari and Indira, published in 2014. Thank you for your attention.